Okay, good afternoon one and all. So today we will start with UJT, Uni-Junction Transistor. So UJT is a special purpose electronic device. It is a 3-terminal device and having 2 layers. UJT is a 3-terminal device. It has 2 layers. So it consists of lightly doped N-type and heavily doped P-type silicon materials. The 2 base contacts B1 and B2 are attached to both the ends of N-type surface. So it consists of 3 terminals. UJT consists of 3 terminals: emitter, base 1 and base 2. Emitter, base 1 and base 2. So the 2 base contacts B1 and B2. So the 2 bases are B1 and B2. So the 2 base contacts are attached to both the ends of N-type surface. It is also called double base diode. So here it has 2 bases, right? So B1 and B2. That's why it is called double base diode. See the block diagram of UJT and UJT symbol on the internal circuit. That is the equivalent circuit of UJT. Okay, see here. So it is a block diagram of UJT. So it is a N-type layer, right? So this one is P-type layer. So N-type layer and P, it has 2 layers. UJT has 2 layers, N-type layer and P-type layer. Here emitter is connected to the P-type layer, and base 1 and base 2 bases are connected to the N-type layer. Okay, so if you see the internal block diagram of UJT, here it has 2 layers. One is N-type and another one is P-type. It has 3 terminals: emitter, base 1 and base 2. So the emitter is connected to P-type and the 2 bases, base 1 and base 2, are connected to N-type material, right? Okay, so here it forms a PN junction. It has P layer and N layer. So that's why here the PN junction is formed. PN junction is formed. Okay, so you can see in the equivalent circuit. You can see in the equivalent circuit. So here we have one PN junction diode, right? PN junction diode. So at the junction of this P layer and N layer, so we have this PN junction diode. So the input voltage is the emitter voltage. Input voltage is the emitter voltage, and the voltage across RB1. Okay, it has 2 resistors, RB1 and RB2. It has 2 resistors, RB1 and RB2. So the voltage across RB1 is V1. Voltage across RB1 is V1. Okay, see here. Emitter terminal is nearer to base 2 than B1. Emitter terminal is nearer to base 2 than B1. Clear? So UJT is a 3-terminal device and it has 2 layers. UJT is a 3-terminal device and having 2 layers. So it consists of lightly doped N-type silicon material and heavily doped P-type silicon material. Lightly doped N-type. So N-type material is lightly doped. So in the P-type material, the doping levels are high. Okay. 2 base contacts are attached to the both ends of the N-type surface, and it is also called as double base diode, right? So UJT also known as double base diode. Here, from the equivalent circuit, the internal resistances of 2 bases are represented as RB1 and RB2. From the internal circuit, the 2 base resistances are RB1 and RB2. Okay, and the emitter terminal is closer to base 2 as compared to B1. Here, the emitter terminal is closer to base 2 than compared to B1. Hence, the resistance RB1 is more than the resistance RB2. See here, the resistance RB1 is more than the resistance RB2. Okay, so RB1 is more than the resistance RB2, right? Here V1 is greater than V2. V1 is greater than V2, right? For example, if the voltage across RB2 is V2 and the voltage across RB1 is V1, so here V1 is greater than V2. This resistance is greater than RB2. Okay, here emitter terminal is nearer to base 2 compared to base 1. So from the equivalent circuit, the internal resistance of two bases are represented as RB1 and RB2. So and the resistance RB1 is more than the resistance RB2. So the PN junction is represented by a normal diode with V gamma. So here you can check the PN junction diode. Okay, see here it is the PN junction. Here the PN junction is formed. So at the input side it has a PN junction diode. At the input side has a PN junction diode. So the PN junction is represented by a normal diode with V gamma as a drop across it. So voltage drop across the PN junction diode is V gamma. Okay, if it is silicon diode, the voltage drop is 0.7 volts. If it is germanium diode, if it is germanium material, the voltage drop is 0.3 volts. So when the emitter diode is not conducting, then the resistance between the two bases B1 and B2 is called interbase resistance. B1 and B2 is called interbase resistance. It is denoted as RBB. So here RBB equal to RB1 plus RB2. RBB equal to RB1 plus RB2. See here from the equivalent circuit. So when this emitter diode is not conducting, this RB1 and RB2 are in series condition. Okay, here if the emitter voltage is 0, then this diode is not conducting. So here these two resistors are in series. So then the total resistance is RB1 plus RB2. That is a base spreading resistance. RBB equal to, we can say that RBB, that is a base spreading resistance. So RBB equal to addition of these two resistors, RB1 and RB2. So RBB equal to RB1 plus RB2. That is the base spreading resistance. Okay. So working. If you see the working, so the voltage V1 reverse biases the PN junction and emitter current is cut off, but a small leakage current flows from base 2 to emitter. Small leakage current flows from base 2 to emitter due to minority carriers. If the voltage V1 reverse biases the PN junction and emitter current is cut off, but a small leakage current flows from base 2 to emitter due to minority carriers. Okay. Second point, if positive voltage is applied to emitter, the PN junction will remain reverse bias as long as VE is less than V1. As long as VE is less than V1. So if VE exceeds V1 by the cut-in voltage V, the diode becomes forward bias. Under this condition, holes are injected into N-type bar. The holes are repelled by B2 and are attracted by the B1. Okay, see here. So from the equivalent circuit, okay, see here. Here we are applying the VBB. So it is the base voltage. So between two bases, between base 2 and base 1, we are applying the voltage VBB. The voltage across RB1 is V1. Okay. The input voltage is the emitter voltage. Input voltage is the emitter voltage. So initially, so V1 reverse biases this diode, right? So it is anode terminal, it is a cathode. Okay. So here V1 reverse biases the PN junction diode. Then the diode is in off state. Okay. So in the initial state, if VE equal to 0, if emitter voltage VE equal to 0, then the diode becomes reverse biased. Okay, if VE equal to 0, so here V1 is applied to this cathode terminal. Okay, so this voltage across RB1, that is V1, it is applied to cathode terminal. That reverse biases the PN junction diode. So if VE equal to 0, the diode becomes in off state. So then only minority carrier current flows from base 2 to base 1. Only minority carrier current. So reverse saturation current. So due to minority carriers only, the current is flowing when the emitter voltage is 0. Okay. So if VE equal to 0, the diode in off state. So only minority carrier current is flowing. Only minority carrier current is flowing from base 2 to base 1. If you apply the emitter voltage, for example, if V1 is 5 volts, see, for example, if V1 is 5 volts, if you are increasing the emitter voltage, if V is 2 volts, still the diode is in reverse biased condition. Okay, if V1 is 5 volts, VE is 2 volts, the diode is in off state. So if we increase the emitter voltage, so when the emitter voltage greater than 5 volts, 5 to 5.7 volts, okay, here V1 is 5 volts. For example, if V1 is 5 volts, up to 5 volts of the emitter voltage, the diode is in off state. When the emitter voltage increases beyond 5 volts, then the diode becomes forward biased. Then the diode conducting. Okay, then the diode conducting. So now the majority carrier current flows through the UJT. Okay, two cases. In the first case, if VE is less than V1, diode becomes reverse bias, right? If VE is greater than V1, then the diode is conducting. And the diode is conducting. Okay. See here. So the voltage V1 reverse biases the PN junction and emitter current is cut off. But a small leakage current flows from base 2 to emitter due to minority carriers, not B1, base 2 to emitter due to minority carriers. If positive voltage VE is applied to emitter, then the PN junction will remain reverse biased as long as VE is less than V1, right? If VE is less than V1, still the diode is in reverse biased condition. If VE exceeds V1 by the cut-in voltage V, if VE is greater than V1, then the diode becomes forward bias. Under this condition, holes are injected into the N-type bar. Holes are injected into the N-type bar. So these holes are repelled by B2 and are attracted by the B1. So these holes are attracted by the B1. Okay. Here B1 is connected to negative terminal. So B2 is connected to positive terminal. So that's why when V is greater than V1, the holes are repelled by the B2 terminal and attracted towards the B1 terminal, since B1 is connected to negative terminal. Okay. So these holes are repelled by the B2 and are attracted by the B1. So this accumulation of holes, see here, accumulation of holes in emitter to base 1 region, so reduces the resistance, right? Reduces the resistance at base 1 and hence emitter current IE is increased. So then the emitter current IE is increased, then the device is in on state. If VE is greater than V1, so immediately the diode becomes forward biased and the holes are attracted towards B1 than B2. Okay. So negative terminal is connected to B1 and positive terminal is connected to B2. So that's why the holes are attracted towards B1 and the emitter current increases. So the resistance at B1 decreases and the emitter current increases, right? So that is the first case. In the second case, if a negative voltage is applied to emitter, if a negative voltage is applied to emitter, PN junction remains reverse biased and the emitter current is cut off. Then the device is in off state. Then the device is in off state. Okay. So if you see the characteristics, see here, if the emitter current is negative, if the emitter voltage is negative, the diode is in reverse biased condition, then there is no current, there is no emitter current flowing through the UJT. Okay, the device is in off state. So only UJT is on when VE is greater than V1. When VE is greater than V1, then only Uni-Junction transistor conducts. Okay. See the characteristics here. So the main property of UJT is it exhibits negative resistance region. The main property of UJT is it exhibits negative resistance region. Negative resistance region. So what is the difference between positive resistance region and negative resistance region? In the positive resistance region, if you increase the voltage, the current also increases, right? But in the negative resistance region, here we are increasing the voltage, the current decreases. See here, x-axis is emitter current and y-axis is emitter voltage. X-axis is emitter current and y-axis is emitter voltage. Okay. So this point is called peak point, peak voltage. This is called valley point, valley point. So in the negative resistance region, if voltage increasing, see here, from this point the voltage is increasing, but the current is going to decrease. This current is going to decrease up to valley point. So this region is called negative resistance region. So here in the negative resistance region, if the voltage is increasing, the corresponding current is decreasing, right? So it decreases up to valley point. So it decreases up to valley point, this region. So after this valley point, it enters into saturation region. So before this valley point, so it is in the negative resistance, UJT is in the negative resistance region. So the main important characteristics of UJT is it exhibits negative resistance region. Okay, it exhibits negative resistance region. So after valley point, it enters into saturation region. Okay. So it is about the working of UJT. Next, if you see the advantage, it consumes low power. So cost is low, it consumes low power, and it has excellent VI characteristics. And the applications are, it is used to generate sawtooth waveform. It is used to generate sawtooth waveform and used as a pulse generator. It is used in switching and timing circuits. Used in switching and timing circuits. Okay. So it can be used as relaxation oscillator. So due to the negative resistance property, the UJT can be used as relaxation oscillator. Okay. So that is about UJT. So next, we will discuss about photodiode. See here, a photodiode is a semiconductor device. It is also a special purpose electronic device. It is a semiconductor device that converts light into an electrical current. It has two terminals, anode and cathode. So see this circuit diagram. A photodiode is a semiconductor device that converts light into an electrical current. Okay. So photodiode is a PN junction diode. So that consumes light energy and to produce the electrical current. So it consumes the light energy and it produces the electric current. So sometimes it is also called as photodetector. Sometimes it is also called as photodetector, a light detector, and photosensor. Okay. So the other names for photodiode is photodetector, light detector, and photosensor. Okay. So this photodiode is designed to work in reverse bias condition. So photodiode is designed to work in reverse bias condition. So it is used in the reverse biased condition. So reverse biased condition means the P side of the photodiode is associated with the negative terminal of the battery and N side is connected to the positive terminal. Okay. So the P side of the photodiode is connected with the negative terminal and the N side is connected with the positive terminal, right? Positive terminal of the battery. So photodiode is a PN junction diode that consumes light energy and it produces the electric current. Clear? See here, when there is no light, the reverse biased photodiode carries a current which is very small and called dark current. So when there is no light, right? The reverse biased photodiode carries a current which is very small. That current is called dark current. So this dark current is due to thermally generated minority carriers. Dark current is due to thermally generated minority carriers. So due to the flow of minority carriers, the dark current is flowing when there is no light, right? When light is allowed to fall on the PN junction through a small window, photons transfer energy to valence electrons to make them free, right? Hence reverse current increases and it is proportional to the light intensity. The amount of current depends on the light intensity. Here the amount of current depends on the light intensity. If light intensity is more, the current increases. If the light intensity is low, the current is also low. Okay. When there is no light, the reverse biased photodiode carries a current which is very small. That current is called as dark current. Okay. When the light is allowed to fall on a PN junction through a small window, photons transfer energy to valence electrons to make them free. Hence reverse current increases. So that reverse current is directly proportional to the light intensity. Okay. So this mechanism is called the inner photoelectric effect. So if the absorption arises in the depletion region, so if the light absorption arises in the depletion region junction, then the carriers are removed from the junction by the inbuilt electric field of the depletion region. Therefore, holes in the region move towards the anode and the electrons move towards the cathode. So holes move towards the anode and electrons move towards the cathode. So the photocurrent will be generated. The photocurrent will be generated, right? So here the reverse current is not dependent on reverse voltage. The reverse current is not dependent on the reverse voltage. So the reverse current depends on the light intensity, whereas in PN junction diode and UNIT diode, it depends on the voltage, right? But here the reverse current, it is operated in reverse bias mode. So reverse current is not dependent on the reverse voltage, but it depends on the light intensity. So if the light intensity is high, the current is also increases. If the light intensity is low, the current decreases. Clear? See here, when a photon of sufficient energy strikes the diode, it creates an electron hole pair. This mechanism is also known as the inner photoelectric effect. Inner photoelectric effect. So those holes move toward the anode and electrons toward the cathode, and then due to the movement of these carriers, the photocurrent is produced. Okay. The total current through the photodiode is the sum of the dark current. So dark current means the current is generated in the absence of light. That current is called dark current. So here the total current through the photodiode is the sum of the dark current and the photocurrent. Okay. So the total current is the addition of dark current and the photocurrent. Here the dark current must be minimized to maximize the sensitivity of the device. See here. So these are the VI characteristics of the photodiode. So and there are different modes of a photodiode. So the operating modes of the photodiode, there are 3 modes. So these are photovoltaic mode, photoconductive mode, and avalanche diode mode. So photovoltaic mode, photoconductive mode, and avalanche diode mode. Okay. So photovoltaic mode, that means, so photovoltaic mode is also known as zero bias mode. Photovoltaic mode is also known as zero bias mode. Next, photoconductive mode. So it is used in the reverse bias. So the reverse voltage application will increase the depletion layers width, which decreases the response time on the junction capacitance. Okay. When it comes to applications of photodiode, so this can be used in, photodiodes can be used in smoke detectors, compact disc players, televisions, and remote controls. Okay. So these are some of the applications of photodiode. Smoke detectors, compact disc players, televisions, and remote controls. Okay. So see the VI characteristics of photodiode. See here in the VI characteristics. So x-axis is the voltage and y-axis is the current. So it is the reverse current. Photodiode continuously operates in a reverse bias mode, right? So there is no forward biased condition. Here photodiode continuously operates in a reverse bias mode. So here the characteristics of the photodiode. See here the characteristics of the photodiode. So here the photocurrent is nearly independent of reverse bias voltage which is applied, right? Here the photocurrent is independent of the reverse bias voltage. The photocurrent is independent of the reverse bias voltage. For zero luminescence, the photocurrent is almost zero, right? For zero luminescence, the photocurrent is almost zero, excluding for small dark current. It is of the order of nanoamperes. If the light intensity is low, the photocurrent is also low. That is in the order of nanoamperes. Here there will be a small dark current. That is in the order of nanoamperes. If the light intensity increases, the photocurrent also increases linearly. Okay, here the if the light intensity increases, the photocurrent also increases linearly, right? So that means the photocurrent depends on the intensity of the light, not on the applied reverse voltage. Applied reverse voltage. So it is about photodiode. See the advantage, the linearity. See here, the linearity of the diode is good with respect to incident light. Here the noise is low. One second. So noise is low. So the response is good. Lightweight, long life, highly sensitive to light. Okay, so these are the advantages of photodiode. So when it comes to applications, so in communications, in optical communications, okay, so for safe equipment, in smoke detectors, in flame detectors, so in industrial purpose, barcode scanners, in the barcode scanners we are using the photodiodes, right? So this is about photodiode and UJT, Uni-Junction Transistors. So with this I am going to stop the presentation. If you have any doubts, you can ask me.